Good afternoon, and thank you for joining us on today's Ethanol Producer Magazine webinar titled The Impact of High Performance Liquid Chromatography Parameters on Monitoring Bioethanol Fermentation Efficiency. My name is John Nelson, Vice President of Operations, Marketing, and Sales here at BBI International and Ethanol Producer Magazine. And I am joined today, and we have the pleasure of chatting with Dr. Brandon Lewis, who is the Biofuels Technical Services Manager at Kemin Biofuels. And one thing I do want to mention is today's webinar is sponsored by Kemin, and just a little bit about them. Kemin Biofuels provides key enzymes and antioxidants to increase the profitability of ethanol and biodiesel plants. In addition to the expanding portfolio of premium products, the Des Moines, Iowa-based team provides tailored customer lab services and technical expertise to help maximize ethanol production and biodiesel stability. So, again, before we get started, there are a few things that we want to go over. Today's webinar is recorded, and you do have the opportunity to go back and listen to it. Or if you want to send it to someone else, they can listen to it as well. And then we will have a Q&A at the end, so please, write your questions in on the side, submit them. We'll answer as many as we possibly can at the end if time allows. And without further ado, I'd like to introduce Dr. Brandon Lewis. Please take it away.
Thank you, John. And I'd like to thank all of the attendees for coming in today and listening to the webinar. Just a little bit about myself. I went to the University of Florida, so I am not native to Iowa, even though that's where Kemin is. But I went to Florida, and then once I graduated, I came to Iowa. Kemin's my first job, and I've been here for 18 years. So as you can imagine, there's quite a few different jobs I've done here, including leading the R&D department, leading the QA, QC department, and before coming to the biofuel side, I was in regulatory. So what I'd like to do today is go over the typical HPLC components that you see in a lab, as well as how these components function. And then we'll end with going over a few experiments where I evaluated just some of the HPLC parameters that I've seen while traveling to the different customers' labs. So when you think about HPLC, like my title was, it's High Performance Liquid Chromatography. It's also been called High Pressure Liquid Chromatography. But everyone has, I'm sure, a certain picture of what an HPLC is. And it's basically, you think about boxes stacked on top of each other. There's tubes coming in, there's tubes going out. And even though it looks just like a bunch of boxes, it's actually very sophisticated, and it does a really good job at what we need it to. So the typical components are going to be a degaster, a pump, a injector, a column, and a detector. And while you may think that the workhorse of the HPLC is going to be the column and detector, but in reality, all of these different components have to work together, and they have to work together correctly for the column to actually separate the molecules and then the detector to be able to analyze them. So the degaster is probably one of the least thought about parts of the HPLC. And what it does is that it removes dissolved gas. So primarily it's going to remove nitrogen and oxygen from the mobile phase. And the reason why it needs to do this is that nitrogen and oxygen, so gases, they're dissolved in the mobile phase. And this really affects the performance of the pumps and the detector, because once you start having bubbles and the gases coming out of solution while it's in the HPLC, you can start having issues. You can see an erratic flow rate. This can be looking like it's a pressure pulses that's coming out of the column. It can also look like different things are wrong with the detector. And in extreme cases, it can cause the pump to actually stop working and stop pumping mobile phase into the column. What it can do to the detector is that, especially with the ones that are light detectors, it can scatter that light from passing through the flow cell, and you can start seeing some ghost peaks. You also start seeing, again, that baseline hard to stabilize. The Degaster, though, in a lot of the new HPLC systems, it's very common, and you'll hear it called either an inline or an online Degaster, and it's integrated to the HPLC. It might be a separate component, or it might be just inside the pump compartment right before the pump. And how it works is that there's a gas permeable tube or a membrane that's under slight pressure in that area, and it allows for the gas to come out of solution, so the nitrogen and oxygen comes out, and it's allowed to pass through that permeable membrane that's under the slight vacuum while the mobile phase stays in and doesn't come out. For older systems, or if you don't have a Degaster, you can do this offline, and the different ways you can do it is either under vacuum. You'll basically have a vacuum flask with your mobile phase and a stir bar, and you'll put that under vacuum, and you can see that the bubbles start forming on the stir bar. They start going through the mobile phase, and that's actually pulling off the gas. You can sonicate it as well. Again, it starts pulling the gas out of the mobile phase, and then one of the better ways to remove the gas is to sparge the mobile phase with helium, and that helium will be able to displace the nitrogen and oxygen. But one of the things you have to think about if you're doing offline degassing is that over time, the gases can redissolve in the mobile phase, and then you're going to start seeing potentially these issues with the pump, the pulsing pressure, and even the baseline stabilization. So once the mobile phase comes out of the degaster, it's going to go into the pump. And there are three primary different types of pumps. You've got the Isocratic pump, the binary pump, and the quaternary pump. And when you think about Isocratic, it's just one mobile phase. There's no mixing. So that's the only thing this pump does is pump a mobile phase onto the column. Now the column, it can pump in a mixed mobile phase, or it can pump in just a single mobile phase, but it can't do anything mixing. When you get to the binary, though, now it can actually pump and mix two different mobile phases. So you can start doing gradients, simple gradients with a binary pump. And then when you get to the quaternary pump, it actually can pump four different mobile phases and mix them. So you can get a lot of really dialed in with the mobile phase conditions that you need. The pump volume, it can normally do, small volumes all the way up to 10 mils per minute, even bigger than 10 mils per minute sometimes. But once you get to those larger volumes, the 10 mils plus, it's generally going to be going into a larger column where you're not going to be worried necessarily so much about analyzing the compound as much as purifying the compound. Most of the pumps today are reciprocating pumps. So they're either a single piston or a dual piston pump. And with a single piston pump, you run into a slight issue in that the piston can only pull in mobile phase and then eject the mobile phase separately. It can't do both at the same time. So you can run into pulsing, and that's going to not allow the pressure to stabilize. So what the manufacturers do now is they put some type of dampening system on there that can help smooth that out. But when you look at the dual piston pump, this isn't really an issue because you've got the two pistons, and as one is pulling up the mobile phase, the other is injecting or ejecting the mobile phase onto the column. And one of the things that I first saw when I came to Kemin that was really interesting was that I was watching my lab manager take apart our HPLC pump and try to fix something. He was either fixing something or cleaning something, I don't remember. But what I thought was really interesting is that those pistons, a lot of times they're sapphire, which I thought was really interesting. And then the valves, they are sometimes rubies that are seated into a sapphire seat. So, like I said, I just found that interesting. I didn't realize that that's what something that the piston could be made out of. From there, you're going to have the injector. And again, the injector is something that people, I think, take for granted just because it's a very robust part of the HPLC, and there's not a lot of problems with it most of the time. It can come either as a manual injector where you have to physically stand at the HPLC, and you generally have a glass syringe that has microliter markings on it, and you pull up your analyte and you inject into the column, and then you close it and it puts it onto the column. This is something in graduate school that I got to do a lot because we didn't really have a sophisticated system. It was just kind of pieced together. And the disadvantage of that, though, is that you have to monitor your time and you have to be ready after the run time is to manually inject your next sample. So it's not as efficient. And then there's the auto sampler, and this really helped efficiency. This one has some type of robot arm. Either it's going to be pulling the sample to the needle, it's going to pick up the vial and take the vial to the needle, or I've also seen some that take the needle to the vial and pull up the sample from there. And you can now get an option of your auto sampler, those trays, to be temperature controlled and chilled. And that's done a lot of times when you have a sample that you're worried about evaporating, and you can chill the temperature, and that helps reduce the evaporation of your sample over time. Going to the column now, this is what we think of, this and the detector, what we think of as the workhorses. These are the things that determine mainly where your compounds are going to be separated and how they're going to be detected. The column, it can come in a few different packing materials. Once they go into the column, they're considered stationary phases, and they can be silica, hydroxyapatite. There are polymeric resins that can be in there. The columns differ in diameter. They can differ in length. And with all of those things put together, you get different types of column types. So the normal phase column is a polar stationary phase with nonpolar mobile phase. And then when you look at a reverse phase column, it's the reverse of the mobile phase, or the normal phase, where you have a nonpolar stationary phase with an aqueous or water miscible mobile phase. The ion exchange is a column that has either anionic or cationic stationary phase that is again used with aqueous mobile phase. And then the size exclusion column, I always kind of found that one interesting in that the sample goes in and it's separated by size. So the larger the sample is, it's not going to really be able to interact with the column. So it's going to have a short flow path relatively and come out first, whereas the smaller particles can enter into the pores that are in the packing material. So they have a lot farther of a path to go through before they can elute from the column, which again, that makes them come out last. And then the chiral column is interesting in that it separates enantiomers. And this is actually a column that we use at Kemin, in that some of the compounds we use are very close together. We can isolate lutein, zeaxanthin, and then there's another compound, mesozeaxanthin, that we isolate. And the transzeaxanthin and mesozeaxanthin are very, very close. The only difference is a shift in a double bond in one of the ring structures, and then the orientation of just one hydroxyl group. So very, very little difference. And up until we were able to come out with chiral columns, those two zeaxanthins co-eluted. So one peak was under the other and you couldn't separate it. But now with the chiral columns, those are something that can be done. And, in case with the column, in reality, what determines your column that you use are what target molecules you want to detect. From the column, the separated sample is going to go to the detector, and there are a lot of different detectors that are out there. There's the UV-Vis, which is able to detect the ultraviolet and the visible spectrum of light. This is, though, slightly more limited than the next detector, which is the photodiode array or the diode array detector. The UV-Vis can only measure one, maybe a couple wavelengths at a time, where the photodiode array or the DAD, the PDA, it can measure all the wavelengths at once. And this kind of gives you a little bit more power than just a normal UV-Vis, because it gives a specific pattern of the compound at the time that it elutes over all of the wavelengths. So a lot of times you can use that pattern to determine what that compound is. You can also use it to determine what the absorption maxima is for the compound, which helps you then to be able to measure it on a UV-Vis at that wavelength. Then we go to the Refractive Index Detector. That's the one that everybody's familiar with in the bioethanol industry that does all the analysis for us. Then you also have an ELSD, a mass spec. There are many other detectors depending on what you want to do. But again, just like the column, the detector is going to be determined by the target molecule that you're trying to isolate. And really, it's not only the column and the detectors, it's the mobile phase, it's the temperature, it's several other factors that are all determined by your target molecule that you want to detect. So what are the target molecules that we want to detect in ethanol going through the fermentation? You've got the DP4 plus peak, which that's also with standards. That can be dextrins. And then you have maltotriose, you have maltose, glucose, lactic acid, glycerol, acetic acid, and ethanol. So the first four are going to be looking more at the sugar profiles, and then lactic, glycerol, and acetic, those are going to be looking at the yeast stress. And then ethanol is what we're really wanting to make. I've got the molecules lined up this way that are kind of from larger size down to decreasing size. And then also these molecules are going to be very polar, and the polarity is going to be determined a lot of times by the hydroxyl groups that they have. Those are the OH groups that you can see here coming off the ring structures. There are also the hydroxymethyl groups. Those are the CH2OH groups that you see coming off the rings. And then there are carboxyl groups, which are one are on lactic acid and acetic acid. And these all help to determine really what the polarity of the molecules are. And these are what help them interact with the column and elute. Now, what you'll see in a little bit later time is that the standard that I'm using also has fructose in it. And fructose and glucose are the same molecular weight. The only difference is going to be a 6-carbon ring for glucose versus a 5-carbon ring for fructose. And then you'll also see, the elution of lactic acid and glycerol, they're very similar weight, molecular weight. So those, there are some other properties that have to be relied on for those to separate as well. The typical HPLC conditions I've seen for ethanol analysis is you're going to be looking at a dilute sulfuric acid mobile phase. And for the column, it's an ion-exclusion or ligand exchange column that's used. And these have some type of size exclusion capabilities. And then the detector is the Refractive Index Detector. So going into a little bit more detail about the Refractive Index Detector, it's a universal detector, so it can almost detect anything. Unlike the UV vis, it requires a compound to absorb light. There's also detectors that require fluorescence to occur, but the universal detector can do anything, whether it absorbs light or not. And there are two different types of refractive index. You can look at the absolute refractive index, which is defined as the speed of light in a specific medium compared to the speed of light in a vacuum. And that's a value. So if you look at ethanol, the value of ethanol is a 1.36. And that means that light passes through ethanol 1.36 times slower than what it does in a vacuum. But for ethanol, what we're really determining is what is the relative refractive index. So relative is meaning that you're going to measure the change in the deflection of light through a sample in a solvent compared to that same solvent alone. And below is it's a really simple diagram of the refractive index detector detection unit. You've got two cells. You've got a sample cell and a reference cell. And the reference cell is going to have your mobile phase by itself. And your sample cell is going to have the mobile phase plus whatever analyte that's coming off the column. If the sample cell and the reference cell are the same, then the light passes through each of those and there's no deflection and it's in balance. Whereas when you're looking at your sample coming off the column, your sample is in that mobile phase and it's different than the reference cell, which only contains mobile phase. So you're going to see the light deflected, and it's that deflection that the RID is going to be picking up. So what does that mean for the RID? It means that it's very picky. And anybody who has worked with one, anyone who has turned one on, has seen just how picky this instrument is. It can only take an isocratic mobile phase. And if you think about it, that makes sense because you have your reference cell that's going to contain your mobile phase that's in the initial part of the run, and then you're going to have a gradient occurring in your sample cell. And so you're going to constantly see that reflection, that reflective deflection of the light going through that sample cell into the reference cell without any type of compound in it. So it can lead to noise, it can lead to ghost peaks, it can lead to stabilization issues. But this piece of the HPLC also, it has long stabilization times because it's very sensitive to temperature, flow rate, pressure, all of those things. If anyone's been the first person to turn on the refractive index detector after it's been off for a while, you're going to see that baseline just goes all over the place. It can go way far high, it can go down low. You can think it's at a steady baseline, but then it starts drifting down or drifting up. And it takes a long time for that to settle down. It's hours. A lot of times for us, we'll leave it overnight, to walk in the morning and have it a good baseline stabilization. One of the things that's interesting, though, with this is that it's really important to completely have your column at temperature. And what I mean by that is just because your HPLC tells you that the conditions have been met with the column compartment doesn't mean that your column is actually at temperature. So, and you can tell this by looking at the pressure, because as temperature increases, pressure goes down. So if the pressure is still going down, then your column isn't necessarily completely at temperature. It's not until that pressure stabilizes that you can be sure that your column has completely reached the temperature that it needs to. And it's also important to flush or purge that cell, because if you change mobile phases or conditions are changed, that reference cell is going to have something different than what the mobile phase is that your sample cell is going to have. So the best time to do that flush or purge is after the equilibrium is achieved. So to just kind of summarize this process, you have the mobile phase that is going through your HPLC, then the sample gets placed into the mobile phase, that goes onto the column, then your compounds elute. And I have in this diagram, I show kind of the reverse of the previous one, where the largest compounds are eluting first, all the way down to ethanol, which comes out last. And these are going through the RID, and then it makes a specific chromatogram that comes out. So for the rest of this talk, I'm showing an example chromatogram of what I'm going to be, really will be all the chromatograms that I'll be showing at the end as far as the order of elution. You have, for the standard, you have dextrin coming out first, then you have the maltotriose at second, maltose is third, glucose is fourth. Like I said, this standard that I'm using, it has fructose, so that's the fifth peak. And you can see, kind of like what I talked about, that the resolution of these peaks is really close together. Those peaks go down to baseline in between, but they have very close elution times. Then lactic acid and glycerol are the next two, and again, you see that same close peak for elution time. And then we have acetic acid, and then ethanol is the last peak. By going to the different plants, I've noticed that most of them are fairly similar, but they're going to have differences between the labs. Sometimes it's the mobile phase. I've seen 5 millimolar sulfuric acid used. I've seen 10 millimolar sulfuric acid used. The pump speed is different. You know, I've seen between 0.3 mils per minute to 1.2 mils per minute. The column, the brand's different. The size is different, and I've seen the columns run at different temperatures with different detector conditions. So I wanted to just kind of see and put a quick experiment together to just see how much impact do these different conditions have on the elution of the compounds that we want to analyze. So what I did is I took 3 ion exchange columns. So these are 3 different brands that I used. I wasn't necessarily looking at different brands as much as I wanted to have significant differences in size and diameter. So I've got a 300 millimeter column with 7.8 millimeter diameter. I ran a 150 millimeter column, so half the distance, half the length, and about 60% of the diameter at 4.6. And then I ran a 100 millimeter column that was back at the same diameter as what we saw for the 300. I treated each of the columns to 3 different temperatures. And I'm not defining the temperature right now because the columns all have different temperatures that the manufacturer recommends not exceeding. So what I did, though, most of the ethanol and methods, the plant methods, are run at high temperatures. So I looked at the highest temperature that was allowed by the column manufacturer, and then I took that temperature and I subtracted 10 degrees Celsius and then 20 degrees Celsius. I'm only going to show you the results for the highest temperature and the lowest temperature, because that middle temperature just kind of fell in between. So I'm not going to go over that one. If there's questions on it, we can go over it at the end, or we can talk outside of the webinar. I used 2 different flow rates. Again, the column manufacturers are going to have recommendations for the max the column can maintain for flow rate. So I took that maximum column and flow rate and the half maximum flow rate that I tested. I tested at 5 millimolar sulfuric acid. I also did 10 millimolar, but I'm just presenting the results for 5 today. And then I looked at low, mid, and high standard concentrations, just with the thought that, do we lose any resolution depending on how high of a concentration of the analytes go into the column? And what I found with these columns and with the RID in general, that it doesn't really, at least these 3 standards didn't impact the retention times or elution of the different compounds that we're interested in. I looked at those same compounds we discussed. Typically there's 8, but the standard had fructose. I thought it was interesting because it's very similar to glucose, so I included that as well. The first slide I'm going to show you is using the 300 millimeter column, and I looked at a 45 degree Celsius temperature as well as a 65 degree Celsius temperature. And for this column manufacturer, they recommend 65 as the highest temperature and 0.6 mils per minute as the highest flow rate. And then I kept the RID at 30 degrees. On the left is the 45 degree column heat, and on the right is the 65 degree column heat. And when you look at them closely, the 300 millimeter column separates all of these standards extremely well. So I'm going to show a little bit of differences just to point them out at the 300 millimeter length that'll be important when we get to the shorter columns. And the first is that the higher the temperature reduces the resolution of glucose and fructose. And these, you have to look closely to see it, but at 45 degrees, it goes completely to baseline. Whereas at 65 degrees, it's slightly above baseline. It's not going all the way down. So it's a decrease in resolution. However, for lactic acid and glycerol, there's actually the opposite. There's an increase in resolution. So this one's a little bit more obvious that at 45 degrees, it's not touching baseline, where at 65 degrees it is. For glycerol acetic acid, there's decreased resolution, but in this case, there's so much distance between acetic acid and glycerol that this reduction in resolution really doesn't matter. It doesn't do anything. It's still well resolved. And then finally, the resolution of acetic acid and ethanol is increased. So, and it increased by, almost a minute when you're comparing it. And, but again, the ethanol peak is so far out that it really doesn't impact. So when you're looking at these temperature effects I showed, just to summarize them, the compounds can react differently. Some of them are going to increase retention times, others are going to decrease. I mentioned that ethanol, the elution time could be a difference of up to a minute. And we're looking at what impact does this have? And it's going to improve the resolution of lactic acid and glycerol. It's going to improve the resolution of acetic acid and ethanol. And then it's going to reduce glucose and fructose and glucose and acetic acid. The improved resolution isn't really that big of a concern, that it's improving the resolution. It may affect how long your runtime is, but there's not really any negative effects. But it's once the resolution starts going down and being reduced that you can start having issues, because you can have peaks starting to coalute with each other, or even if they're not completely coaluted, then they might be too close and don't go back to baseline. But if the peaks are large, then it doesn't matter because there is plenty of separation between the peaks. So what does flow rate do for the 300 millimeter column? And on the left, we have 65 degrees at 0.6 mils per minute. And on the right is the same temperature, but at 0.3 mils per minute. And what's interesting is that the chromatographs look the same. There's the same ratio of distance between the peaks. And it's something I really didn't expect. I anticipated that I would see some kind of difference. But in reality, these peaks are exactly half the time for the 0.6 mil per minute as it does at the 0.3 mil per minute. And really what you're doing, at least on this column, is you're only delaying the length of time that you can do your next sample. So you've got 21 minutes at a 0.6 mil per minute flow rate, and you've got almost 42 minutes at half speed. So, in this case, like I said, you're just delaying the time that you have till the next injection. So what happens when we go to a smaller column that is, in this case, half the length and then about 60% of the diameter? So the 300 millimeter column is on the left and the 150 millimeter column is on the right. And I'm just comparing the 60-degree range temperatures with these just because that's the max temperature for the 300 millimeter, but you'll see higher temperatures for the 150 as we go. And, it's just kind of obvious on some of these changes. You've got the more complex molecules, the resolution isn't as good. They don't go to baseline anymore. You've got, with glucose and fructose, there is virtually no difference. You see a small shoulder coming off that might indicate that it indicates that there's another compound under that peak, but you don't see it at all. And the same thing happens with lactic acid. You don't really even see a shoulder on this one between lactic acid and glycerol. The acetic acid has gotten much closer, but it is still separated by baseline, and ethanol comes out at 4 minutes. So you're really talking about a much faster runtime with ethanol with this shorter column than if you were using the 300 millimeter column. And if your goal was really just to get a measurement on ethanol and not the others, you can have a very quick turnaround time at 4 minutes a sample. So what does temperature do when we're talking about the same column? The 60 degrees compared to the highest temperature of 80 degrees that's recommended. For the larger sugars, there's not really that much difference. But because temperature, even in the 300 millimeter column, was reduced the resolution between glucose and fructose, you can see here that resolution is completely gone. There's not even a shoulder. But with lactic acid and glycerol, where you didn't have anything before, now you've got a pretty good shoulder. So it's starting to pull out the lactic acid, but it's not there yet. And then when we look at the glycerol and acetic acid peak, you can see where the detriment is really coming in, and that now we've got a peak that doesn't go back down to baseline from glycerol going to acetic acid. But then ethanol, there is no issue still with the ethanol peak. So how does flow rate work? In the 300 millimeter column, we didn't really see a difference. But at the flow rate of 0.6 and 0.3, now at that lower flow rate, we're really starting to see differences. You've got an impact on the larger sugars, you have a much greater impact on the fructose and glucose. This is almost a separate peak now. And then there's a little bit of difference with improvement with lactic acid and glycerol. We now have basically the same separation for acetic acid and ethanol. That was at the lower temperature. So what happens if we take it to the higher temperature? We see a little bit more improved of the larger sugars. The maltose is getting closer to baseline. We see less improvement with the glucose and fructose of what we saw at 60 degrees, but it's still better than 80 degrees. We're seeing decent separation between lactic acid and glycerol. The auto-integrator, it could probably, just like here, it can drop a line down to baseline and get a pretty decent area there. The separation of acetic acid is now back to baseline, and then we're still okay with ethanol. If we switch to the 100 millimeter column, what's really interesting is look at the time on the bottom of the chromatograms, and the 100 millimeter column on the left actually is taking almost double the time to elute ethanol as it did on the longer 150 millimeter column. And if you remember though, the diameter of the 100 millimeter column was larger than the 150 millimeter column. If we compare the 100 and the 150, you've got a little bit more impact on the separation of glucose and fructose. There's a little better separation, not much between lactic acid and glycerol, but they're not there at all. A little bit more separation of acetic acid. And, the ethanol peak is still by itself. It shouldn't be an issue to integrate. What about temperature? We're looking at the maximum temperature for this column was recommended at 65 degrees. And so the minus 20 of that maximum was 45 that I ran. Not very much impact on the larger sugars, but when you look at the fructose and glucose, just like in the other columns, the resolution is better at the lower temperature than it is at the higher temperature. We have slightly better resolution between lactic acid and glycerol at the higher temperature. You can see it's a little bit of a shoulder there, but not anything great. And there's not really an impact in acetic acid and ethanol. If we drop that flow rate, though, we do see another impact. So we saw the same impact at the 150 millimeter column, that both of these are different than the 300 millimeter column, and that there wasn't really much of a change. We don't see much difference with the larger sugars, but when you look at glucose and fructose, the fructose is still better separated at the lower flow rate, but there is no help with the lactic acid and glycerol. And then we still don't have any issues, any changes with acetic acid or ethanol. If we look at the higher temperature with the flow rate change, again, we still get no real change in the beginning. The glucose and fructose, it is better. The lactic acid and glycerol, still there's no change. So this is different than what we saw with the 150 millimeter column. And then there is, everything is fine still with acetic acid and ethanol. So what are we looking at as far as a summary for these experiments? For these specific columns that we tested, I looked at the 300 millimeter, the 150, and the 100 millimeter column. So with these columns and these conditions, the 300 millimeter does a great job of separating all 8 compounds of interest, and then throw in the 9th compound, fructose, which isn't followed that much, but it does excellent separation with there. And the flow rate doesn't really impact it at all. The same resolution was there at the 0.6 mil per minute flow rate, which is 21 minutes, compared to the 0.3, which is 42 minutes. And the only thing that's going to this do is to increase the amount of runtime between your samples. Temperature, even at the 300 millimeter column, can matter. If you look at it, there are slight changes, but there were some peaks where the resolution reduced enough that the baseline was not achieved between the 2 compounds. For the 150 and 100 millimeter columns, we always had a pretty good complete separation of acetic acid and ethanol. With 150 millimeter column, it was 5 to 10 minutes. For the 100 millimeter column, it was 8 to 16 minutes, depending on the flow rate. And there was the high impact. We saw that there were significant changes in the peak elution times and how well they resolved from other peaks. But even though temperature did have an impact, I'm going to put on here that temperature may not really matter, but it's dependent on your goal. Because no matter what conditions we had running with the 150 and the 100 millimeter columns, we never separated really any of the other compounds except for acetic acid and ethanol. So if you're really just wanting to get ethanol as fast as you can, that 150 millimeter column that can give you ethanol in 4 to 5 minutes, that would be a great choice. We probably could change some more conditions and get the others a little bit further resolved from each other. But in order to do that, you're already up to 16 minutes, let's say, with the 100 millimeter. And now we're getting really close to what the 300 millimeter column times are. And we know we can get complete separation of those compounds in that column. Although I have seen there's a column I have worked with that is the same 300 millimeter length of column. And because of the higher temperature it can run, we typically run it at 80 degrees with that larger length. It can get ethanol out by 12 minutes. So it may still be better to use those longer columns if you want to resolve all of your peaks. So the whole Kemin Biofuels team, we'd like to thank you for attending this webinar. Hopefully it was interesting to you. You learned some things. If you have any questions outside of our question and answer time, feel free to contact all of us or any of us, and our contact information is on there. You can also reach us through kemin.com biofuels, and please feel free to follow us in the different media outlets. So thank you again.
All right. Thank you, Brandon. Appreciate all your information. We do have some questions that have come in. And I think this question actually came in, excuse me, roughly around slide 14 or 15. You showed a graph. And the question that came in was, why is there always a big mobile phase dip right before ethanol peak on any H+ column? And then they also wrote, right at the methanol and 2 to 3 butandol retention time.
You know, I've actually never looked at these columns with other of the solvent standards, the other alcohol standards. I know in my columns that in these, I don't know if I really showed a big dip in the peak, so I'm not necessarily sure maybe what they're describing. I didn't see it. Maybe it comes out with the sample, but I'm sure that if you'd like to send me an example chromatogram, I'd be glad to look at it and see what it might be. The column manufacturers, they're also a great source of information that you can, talk to them as well and see what that might be.
Great. Another question that came in here. Why does adding helium to the mobile phase not cause issues with degassing?
So this, when you think about it, it's definitely counterintuitive to what you would think, that you're putting another gas into a mobile phase to remove oxygen and nitrogen. So to me, I agree. It just, I can't necessarily wrap my head around why it happens, but what really is occurring is that the solubility of helium, it's very low, so that it can push out the nitrogen and oxygen, and anything that might remain in the in that mobile phase isn't going to really cause outgassing problems. One of the interesting things is, looking at the various ways of doing the degassing. We just need part of the gas to come out. We don't need the full amount. And, I've seen that even if you can get 50% of the gas out of there, that won't cause degassing issues.
Okay, great. Thank you. We have another question that came in. What 300 millimeter column are you using?
I've tried a different one, several different ones. I don't necessarily want to call out a brand here, but if you'd like to contact me, I'll be glad to talk to you about it and go over some of the columns that I've tested.
Okay. We also had another question that came in from the gentleman. We'll send that over, and you can chat with Patrick directly. So we do have some other questions that we want to get to. Why does column pressure go down as temperature increases?
So generally, when you heat a fluid, the viscosity is going to decrease. And because the viscosity decreases, the pressure is going to decrease on the column. So it's really the solvent viscosity is what's going to determine the pressure on the column. And with these the increases in temperature and the decreases in pressure, you can actually start increasing the flow rate. So, which will make the runs a little bit faster. But, as we saw in this presentation, that can still have either some beneficial or detrimental effects.
Okay. Why does temperature affect resolution?
So the really simple answer is that retention factors and selectivities of compounds are going to change with temperature. So it means that they basically could have more or less interaction with the stationary phase or the mobile phase, and therefore it's going to change how long they retain on the column. However, this is really unique to the molecule, and as we saw in the presentation, the different things can happen. Sometimes resolution is increased, sometimes it's decreased. So it's something really that you want to pay attention to.
Okay, great. We have another question that came in from Eduardo. Thanks for sharing the information. It was very interesting. Have you published those results?
No, I have not published these.
Okay.
I have not published them. There are some publications that you can look at that are out there. They aren't necessarily looking at column temperature on column length and flow rate all at the same time, but there are some looking at those individual conditions. So I'll be glad to forward you those references. I'll have your contact information and I can send those to you.
Okay, great. What impact does sulfuric acid concentration in the mobile phase have on elution of peaks?
So this one is an interesting one in that, again, it depends on the compounds. But for some of these compounds, changing the concentration of the sulfuric acid, I did some of these experiments. I didn't show them just for time. But for example, taking it from 5 millimolar to 10 millimolar of the sulfuric acid mobile phase can actually have almost the same effect on the compounds as the temperature, as increasing temperature. So in some cases, I could cause the same separation by increasing the sulfuric acid as I could by increasing temperature. But again, it has to do with what molecule, and different ones will react differently.
Great, thank you. Another question that came in, what impact does the temperature of the RID have?
This is another thing that I did look at in this experiment, but I didn't present these results because there really wasn't a difference. So I looked at 30 degrees, 40 degrees, and 50 degrees Celsius, and really didn't see anything. If I'd gone higher, maybe I would have. But if you think about what we're actually measuring for the refractive index, in this case, it's the relative refractive index. And so the reference cell is going to be at the same temperature generally as the sample cell. So that relative difference isn't going to really change. But the column, or having the RID maintain a constant temperature, is the important part. Not necessarily the temperature it is, but make sure it's the same, because that can affect that instrument because of how picky it is.
Thank you. All right, we have time for one more question. We have a question that came in from Victor. How important is the pH of the mobile phase? Should the mobile phase be used according to manufacturer's recommendation?
So, the mobile phase, the pH has a lot to do also with the concentration of sulfuric acid. So if you look at, let's just say 10 millimolar sulfuric acid, that's going to have, I think, a pH, let's just say, of around just under 2. Let's just say just under 2. I don't know if that's exact, but it's low like that. The pH at 5 is going to be 2.3, let's say. I think it's actually 2 and 2.3. And then there are some of the different studies that I've seen that use a 0.5 millimolar sulfuric acid solution, and that's going to have about a pH of 3. So in those studies at the lowest level of sulfuric acid, they had a little bit better resolution on a shorter column than what I saw here, but I don't know if it was some of their other parameters they did, or if it was just that sulfuric acid concentration. So that concentration is going to be what makes the pH. We're not doing a buffer. There's no adjustment of the pH, so that's what you'll see. And it's going to have similar impacts that are, kind of compared to temperature.
Great, thank you. We appreciate it. That is all the time we have for questions today. We appreciate you being on today. And it was a lot of outstanding insight and information, and I know our attendees appreciated everything you shared. In regards to the information, again, this is being recorded, so if you do want to go back and review something, we will make this available. Some of the questions that were asked were not, we weren't able to get to all of them. We will be forwarding those on to Brandon and team, and they will be responding to you directly. And so expect that information coming in the coming days. Again, we want to thank Kemin for being today's sponsor. Please visit them. And I do want to make a couple, I do want to talk a little bit about some of the upcoming events that are happening. We do have the International Biomass Conference and Expo happening next week, and that is a virtual event, and that's March 16th through the 17th. So if you are interested in taking a look at the biofuels industry, we've got a great lineup of speakers at that event. And we've got a very jam-packed expo hall as well. So 2 days of full content ranging from biomass power and thermal to pellet production to advanced biofuels and biogas and RNG. So it's a lot of great information. So if you want to know what's going on in the biomass industry, all things biomass, please check us out next week. We also have the International Fuel Ethanol Workshop and Expo coming up. And the big news that some of you have heard and maybe some of you haven't is we are moving from Minneapolis to Des Moines, Iowa. And that move is is currently taking place. However, we have announced it, and it's happening, and that is happening July 13th through the 15th. So we did keep the same dates. So if you did have that on your calendar already for July 13th through the 15th in Minneapolis, we have now moved it on the same dates to Des Moines, Iowa. So be on the lookout for more information on that. Also co-located at that event is the National Biomass Summit and Expo and the Biodiesel and Renewable Diesel Summit. So you'll be seeing a lot more information coming your way in the coming months. If you do have questions, please reach out to us. And with that, we appreciate you being on today's Ethanol Producer Magazine webinar, and we look forward to seeing you in the future. Thanks again.